All right, hello, and excuse me. Welcome. I am back. This is office hours, and we're ready to get going. So, yep. Okay, just checking everything is. Live on the stream. So my one question is, what are your questions? We'll have the time to get into all of it, hopefully, within the next 3 hours. So I'm going to start just booting up some stuff. Usually there's questions with respect to Canvas stuff, with respect to exam stuff, and so I'm just going to start opening things until you ask me what's up. Yo, practice homework 677. Let's get it. All right, let's take a look. Okay. So let's see, we got a string of homework questions. Actually, Carenza, your lab question I think is going to be a quick strike. So I'm just going to open this really quick. Okay. Okay, so Carenza, actually, I just wanted to look up the table that you were asking about just for reference. Actually, the driving force, that thing that they're calling the driving force that they're looking for, will will always be the product that is included in the net ionic equation. And the reason for this is because that product formation is what causes the reaction to occur. All right. All right, Susan, you had a question about chapter 6, number 77. Whoa. I'm trying a different thing with the mic. I feel like we had a little better. That I've been messing around with the settings to. There's that high-pitched feedback, like sound that just drives me nuts on the videos. And I don't hear it when I'm live casting. I only hear it when I go back to add the timestamps to the videos, and so that's, I assume, what you guys are hearing. Not assume, I know that you guys are hearing it. And so I've been trying to fix it. We had a little bit better success with not having it as much or as prevalent when I live cast from not my house. And so I'm trying a different mic setup rather than having it like mounted on an arm. It's resting on the table, but as a result, you hear that whenever hear the pages. Turning pages, the mic picks it up because it's in direct base contact with the desk. So anyways, sorry, that was a non sequitur. Susan, you have a question about, oops, about chapter. So this is chapter 6, homework number 77. Sorry for the throat clearing. Okay, so let's let's go ahead and do this problem. So both water and sulfur dioxide are products from the reaction of sulfuric acid with copper metal, as shown by the following equation. How many grams of HCl will be produced at the same time that 25 grams of potassium bisulfite is produced? Okay. Oh wait, no, I jumped questions. How many grams of water will be produced at the same time that 10 grams of SO2 are produced? So they give us a balanced chemical equation, which is awfully kind of them. Oops, it's on a C, there we go. 2 moles of sulfuric acid react with copper metal to produce SO2 plus 2 molecules of water plus 1 molecule of copper 2 sulfate. All right, and they tell us that 10 grams of sulfur dioxide is produced, and they ask how many grams of of water will be produced. All right, and so this balanced chemical equation tells us, I'm just switching up my colors here, that for every 2 moles of water that are produced, 1 mole of SO2 is also produced. And so what we need to do here is, we're told the mass of sulfur dioxide that's produced. We need to know how many moles of sulfur dioxide is produced, and then we can convert from moles of sulfur dioxide to moles of H2O. All right, so this is just a stoichiometry unit conversion problem. We're given 10 grams of sulfur dioxide. And here we need to multiply by our molecular weight of sulfur dioxide to convert from grams of SO2 to moles. I'm just going to do my whole setup, and then we'll go back and figure out what our conversion factors are. So the first step is we want to convert from grams to moles. Next, we convert from moles of sulfur dioxide to moles of water. And this unit conversion comes straight out of the balanced chemical equation. 1 mole of sulfur, for every 1 mole of sulfur dioxide that is produced, we will also produce 2 moles of water. And then finally, we need to convert from moles of H2O to grams of H2O, and we use the molecular weight here. We use the molecular weight here. To convert from moles of H2O to grams. So we have a couple molecular weights to calculate, and then we can crunch our numbers. First, sulfur has an atomic mass of 32.07. Oxygen has an atomic mass of 16.00, but we have 2 of them in this molecule. So we have to multiply by 2. Now together, 16 times 2 is 32, plus 32.07 gives us a molecular weight of 64.07. 7, and that's what we plug in here. All right. Next, next we need to determine the atomic mass, the molecular mass of water. Hydrogen has an atomic mass of 1.01. We got to multiply by 2. Oxygen has an atomic mass of 16.00. So when we add these two together, we get a molecular weight of 18.02. And that is what we punch in here. Sorry, that's a 2, not a 7. All right. So now we can cancel our units. Grams of sulfur dioxide cancels grams. Sulfur dioxide. Moles of SO2 cancel moles of SO2, and moles of H2O cancel moles of H2O. Okay, cool. Okay, so here, let's see, we got 10 divided by 64.07. Well, 10 divided by 64.07 times 2 times 18.02. Oops. Sorry, times 18.02. Sorry, I messed up on my calculator. I gotta add these things, or not add, enter these things again. So the number that my calculator is giving me is 5.625097. We can only keep 3 significant figures because of our mass only has 3, and our molecular weights each have 4. You gotta go with the least. 5 will round up. So 5.63 grams of water is the mass of water produced alongside 10 grams of sulfur dioxide. Okay, so Susan, I'm awesome. I'm awesome. Susan, I'm awesome. Susan, I'm glad that you were able to find your mistake. It is awesome. Working my way down the list. Okay, so actually, before we hit the next couple of questions, Parthana, you have a question that actually I've gotten a couple emails that I've had a chance to glance at, but haven't had a chance to respond to. Your question of will we be able to get answers to the quizzes that you've taken, so that you can know what you've done wrong. And this is actually something that I've been in dialogue with the other adjunct instructors about, because it's a question that they've been circling around too, and we've kind of been talking, putting our heads together, and unfortunately the answer to that question is no. And the reason why you won't be able to see the answers to quizzes and or exams is because we've already seen answers to so there are some answers that we have made available, or other instructors have made available, I should say, to assignments that we've created. Other instructors have made answers available, and we've actually already seen those answers start surfacing on websites that students use to kind of stockpile answers, use answers for the point of I'm sorry, I'm hesitant to use the word cheating, because part of it is, part of it is that, like I say, like my exams, my quizzes, my stuff are open, internet open, textbook open, open everything, open internet, open other people, and I am totally fine with that. But that, and part of the reason why I don't put any restrictions is because, like, I can't control it. Like, during a normal semester, I give my exams during the lecture period. So everybody rolls into a room. The rules are you can't open your phone, you can't, open a textbook. You just have to sit there and take the test. And then at the end of the day, you take it, you finish it, and that's that. But with the internet, I put no restrictions on it because there's nothing to stop anyone from taking a screenshot, from going online, from looking for things. Like I one way professors are using one way of monitoring exams is professors are having students all link into them with Zoom, and you have to have a webcam open, or you have to screen mirror your computer so that the professor can see what you're doing on your computer and what you're doing like physically right there, and you have to stay there in front of the webcam, and if you make any slight move they could fail you for if they perceive you to be cheating during the exam. And I don't do any of that because I think that there are privacy concerns, which I totally get. There are accessibility concerns. Not everybody has good enough internet to do all that streaming and screen mirroring, and I don't want it to be limited to students who may not have access to that sort of either internet service or technological capacity. And so I feel like, so because of that, the exams are open everything, but because we've already seen, there are students in our classes, and I don't know if they're in my section or in the other instructors section, but that are already like stockpiling and trying to proliferate answers to things online. That's the reason why I can't make them available, because once I do, then a person takes the quiz or exam or whatever and then takes all the answers to theirs, posts them online, and I mean, even though I still use problem banks and all that stuff, it's just a layer of security that I'm not willing to compromise. Especially because, like, with the lab quizzes, sometimes there aren't problem banks, or sometimes the problem banks are very small, because I don't write them always, and so because we know that students are, and I'm not accusing anyone in particular, but someone is taking the answers in these other classes and posting them for the express purpose of students not, because, like, what's the point of the quiz? The point of the quiz, the lab quizzes, are to test to see, okay, you had to watch this video, you had to do these calculations, did you understand them, did you remember them, did you, do you know them enough to do them? And if you can look them up and find the answers and then just punch them in, it hasn't proved that you've learned anything at that point. And so that's the reason why we can't make them available, is because other instructors this semester were, and then they were surfacing kind of on these sites that are there for the express purpose of, to defeat the purpose of learning, right? To defeat, these sites kind of exist to just proliferate answers so you can get grades without gaining knowledge. And so it totally sucks because normally in a normal class setting, and you see, Prathana, I can't do that either. I can't give you the answers after the due date because, guess what? I'm still teaching in the fall. People are still going to be teaching, possibly using this material, these quizzes, in future semesters. So yeah, if I made them available after your particular due date, you wouldn't be able to, but it just takes one person to leak them online, and then they're in, a problem bank, and then students, I'd be doing my future students a disservice, because some of them would be working hard and taking them honestly, and then others would be finding these websites, finding these answers, just copying and pasting them, and they would be scoring higher than the students who are working for it, even though they're not. So Unfortunately, and I don't know how many people are doing this. Yeah, totally. It sucks. It totally sucks. Because my guess is that it's a minority of students, like a small percentage of students. That's just based on my gut. That's based on the fact that I really like you guys, and I don't think any of you guys are. And not that I'm asking, but usually with this sort of thing, it's a small percentage of the population of the class that are attempting to leak grades and stockpile this kind of hoard information like that. And what it does is the precautions we have to take to prevent that from happening end up hurting the majority of students who would use it honestly to learn. So anyways, that's it's been a long dialogue with the instructions. I know these types of questions on the questions about will we be able to see these responses have come up for a while, and there have been a round of emails kind of going back and forth between myself and the other faculty. And anyways, we recently kind of all came around and realized what was going on, and that's the decision that's been arrived at. Okay, so a couple things. Yeah, it totally sucks. Say, Prathana and Susan, you both raise totally solid questions of what happens if there's typos on the quizzes or exams, which could totally happen, right? You're like, how do we know? How are we going to catch them? So one thing, you guys tend to actually be pretty good at catching them in the moment. You're like, I'm pretty sure this is the answer, but I marked it and it came back wrong. And so like people usually email me, and that's one way that they're caught, but that's not the only thing that I do. I mean, so it's you know, I do proofread them beforehand, so I try to catch all the typos. There usually are some that eke through the cracks, and for those ones that I don't catch, and that you don't catch while you're taking the test, not everybody does. I am able to catch those retroactively because Canvas has very good analytics and statistical analysis of your problems post-exam. So what I do is I go in there, and it's really easy to spot, actually. It's really easy to spot when you go in, because I get to see like the total average, right, of everybody. But Canvas has a statistical breakdown by problem, like by specific problem, and I know the typos when I see the numbers on the stats, or not necessarily, but there's a red flag when a problem has a statistical average that is crazy low, much lower than the average for the normal test. That's when I know one of two things have happened. Either it was a wicked hard problem, so most students are getting it wrong, or there's a typo. Usually the second one. They usually end up being typos. And so for those ones that I see that type of dramatic deviation, I even check out the ones with moderate deviation from the average because I'm just paranoid about there being typos. So I will look into each one of those problems, redo the calculation to make sure that the correct answer was actually correct. And when it's not, then I go in and credit the class with points for those typos. So, and it's actually the statistical analysis of the problems after the exam are better. It's a better way of catching typos than even pinning it on individual students, because usually what happens, this happened to me last semester when everything went online and I started doing online stuff, is students would usually catch some of the typos but not all. And so like I would get emails about like, what about question 4, or there's a problem on question 17 or whatever, and I'd look into them, and sometimes they would be, sometimes they wouldn't be. But of all the ones, if there's like a circle where like everything in the circle is the typos student would catch, there'd be a larger circle of, based on the statistical analysis, I would find those anyway and find other ones that they wouldn't catch. So all that to say is I do my best to catch all the typos before the exam goes live. But for the typos that do exist, I analyze every test in retrospect, and the tools that Canvas provides allows me to find the problematic problems, and then I manually credit you guys after the fact. So I understand that is a concern, but don't let that be a concern to keep you up at night, because I do due diligence, but to the best of my ability before, but then afterwards I catch every single one and give that back to you guys. So I understand that human error is a source of concern, but the statistical analysis allows me to beat my own. Yeah. And Parthana, you can totally, if you suspect there's a typo, totally email it to me. I so appreciate that input. And yeah. Say you are welcome. It's my job to be your instructor and to make this as fair a learning environment that I can for you guys. So I appreciate your appreciation a ton. But it's also my job. It's what I'm here to do. Okay, so you were asking, what about Lab 8's page? Oh, sorry. Yes. Sorry, it took me a moment to understand that. And I know I've kind of I've been talking for a while, and we have more problems to get to. But to say, and everybody else, I will be soon. Say was asking about when Lab Experiment 8's page is going live. I will most likely be posting those tomorrow, Lab 8 and Lab 9. And if you've looked at the syllabus, Lab 8 and Lab 9 are due tomorrow. I feel like I built up where I was like ahead of things, and then the holiday weekend kind of pushed everything back because I wasn't working, and so I'll be posting those tomorrow. But also, I just want to let you know, if you're like the type of person who likes to work ahead and you're a little anxious about it, I'm also planning on pushing back the deadlines for 8 and 9. So, because it's like post it Friday, one's due Tuesday, one's due Thursday. And you're taking an exam that's kind of in rapid order. You haven't had a chance to work ahead on it. So I will be pushing back. I haven't picked the dates yet, but I know I'm planning on putting the due dates for Lab Experiments 8 and 9. I'm going to make them a little later because I am later kind of getting the videos and all that stuff kind of packaged and to you. So you'll have more time to work on it if you were worried about that. They're due Tuesday and Thursday. Yeah, totally. I'm going to be posting an announcement where they're going to be due later, and you'll notice the due dates for like the quizzes and the submission. It'll be at a later time. They'll be due after their currently posted due dates. You are welcome. And you also have bigger fish to fry, right? You've got an exam on the horizon, which will probably be taking more effort and energy than those lab things. Okay, I'm going to scroll back up to the top of the thing because I know there are other example questions, but that was our long, probably overdue convo about quizzes, view and stuff. Also, I have been meaning to post about labs 8 and 9. Not only post them, but post about the delay in their due dates for a bit. It's just been a crazy last 5 days. Okay. Okay, so we have a couple other requests from Chapter 6. Chapter 6, problems 79 and 85. We'll start with 79. Okay, oh wait, that's 77. 79. How many grams of beryllium are needed to react completely with 45 grams of nitrogen in the synthesis of Be3 and 2? Okay, so here they don't give us, they do not give us a balanced chemical equation. They just say that beryllium and nitrogen react to make this guy. So it's up to us to balance. Fortunately, this isn't the worst thing in the world to balance. We just need 3 berylliums on our reactant side. And so, let's see. So we're asked to find the mass of beryllium. How many grams of beryllium are needed to react with 45.0 grams of nitrogen to make this product. All right. So again, we have another situation where we have a mass of nitrogen. This time they're asking about how many grams of our other reactant are we going to need. So grams of reactant, we're asked about grams of our second reactant, not grams of product. But the process is exactly the same. We're going to take our, not 4.5, our 45 grams of nitrogen. And we're going to start, we know the mole to mole ratio, right? We know that 1 mole of nitrogen reacts with 3 moles of beryllium because that's our balanced chemical equation. But we have to start by converting our grams of nitrogen to moles. All right. And again, we'll come back and calculate those molecular weights later. Right now, I'm just setting up all of my conversion factors. So we put moles of nitrogen in the denominator, moles of beryllium, just atoms, in the numerator. This is a 1 to 3 molar ratio, and again, that comes from our balanced chemical equation. And now we need a conversion factor to go from moles of beryllium to grams. And the cool thing about this one is beryllium is just an element. So we can look up Be on the periodic table, and 1 mole of beryllium has 9, whoa, that's the weirdest 9 I've ever written, has 9.01 grams of beryllium. All right. So we just have to calculate our molecular weight of nitrogen. Nitrogen has an atomic mass of 14.01 that we simply multiply by 2. So it would be 28.01 grams of nitrogen in 1 mole. Grams of nitrogen cancels. Moles of nitrogen cancel. And then moles of beryllium cancel, leaving us with grams of beryllium. All right, so now we can punch in our, crunch our numbers. 45.0 divided by 28.02. Sorry, I wrote 0.01 here. I have no idea why I did that. This should be a 2. There we go. Times 3 times 9.01. All right, this, my answer, my value is 43.410 0642, I guess. And, but I can only keep 3 significant digits. So I count them off, 1 will round down. So my final answer will be 43, we need 43.4 grams of beryllium to react with 45.0 grams of nitrogen. All right, and that is, excuse me, chapter 6, number 75. Next in the queue is a third request coming out of the chapter 6 practice homework. So we have chapter 6, number 85. All right, let's see. If 125 grams of calcium nitride were produced from 29 grams of nitrogen and excess calcium, according to the following reaction, what is the percent yield of calcium nitride? All right, first things first. They give us a balanced chemical equation, which shows 3 moles of calcium reacting with 1 mole of nitrogen. Sorry, I just like to make these colored. 3 moles of calcium reacting with 1 mole of nitrogen to produce 1 mole of calcium nitride. All right. And they tell us that they give us a couple pieces of information. They tell us we start this reaction with 29 grams of nitrogen, all right, N2. We have that much to start. They tell us also, they give us our actual yield. All right, our actual yield for calcium nitride is 125.5 grams. And look what they ask us to find. They want us to find the percent yield. All right, they want us to find a percent yield. And this is all of our given information up above. There's one last piece of information we'll need to solve this, though. We need to know what the equation for percent yield is, and it is the ratio of the actual yield divided by the theoretical multiplied by 100. Right? Turns out we have our actual yield. In order to find our percent yield, we are going to need to determine our theoretical yield, because they don't give us the theoretical yield. They don't give us the theoretical yield, but they do give us the mass of nitrogen that we start with. So we can use our mass of nitrogen gas to determine our theoretical yield. Then we plug it into this equation, and we're off to the races. All right? So we got to start by taking our mass of nitrogen, N2, and multiplying it by dividing by the molecular weight of N2, so that we can convert from grams of nitrogen to moles of nitrogen. This will allow us to convert from moles of nitrogen to moles of calcium nitride. And then we multiply again, or not again, for the first time we multiply by the molecular weight of calcium nitride, and this will give us our theoretical yield. So this right here is our theoretical. All right, we have a couple of molecular weights to calculate. Nitrogen has an atomic mass of 14.01. We've got 2 nitrogens in N2. So this is an atomic mass of 28.02 grams per mole. Our mole-to-mole ratio from the balanced chemical equation is a 1-to-1 ratio. So we plug that in there. And then we need our molecular mass of calcium nitride. Calcium has an atomic mass of 40.08. nitrogen 14.01, but we have 2 nitrogens in play, and we have 3 calciums in play. So we multiply 40.08 times 3 plus our 28.02 for our mass of nitrogen. This gives us a total molecular weight of 148.26. All right, we are ready to crunch our numbers to determine our theoretical yield. I'm going to make a little space down here. So our theoretical yield, let's see, will be 29 divided by 28.02 times 148.26. All right, so the theoretical yield will be huge. It'll be 153 grams of calcium nitride. All right, now that we know our theoretical yield, you got that denominator, we can calculate percent yield. Our percent yield is equal to actual over theoretical, 125.5 grams over 153 grams times 100. 125.5 divided by 153 times 100. Let's see, and we can keep 3 sig figs, right? So this will be 82.0% is our percent yield of calcium nitride. So again, you want to base this off of the chemical equation, the algebraic equation for the quantity you're trying to find. Here we're trying to find percent yield, actual over theoretical. We realized we were given actual. We had to calculate theoretical and then brought everything together for the happy ending we all deserve. Okay. All right. I'm 3 comments in. Moving to number 4. Okay, we did that. Can I give an example of a question on lab quiz 9? Okay. Sorry, I gotta rearrange my keyboard. Sorry for that loud thud. Okay, Esther, sorry, I'm just now seeing your questions up top. So first with lab 7, the precipitate for water are all so Esther's question about, again, lab number 7 was, she asked, so the driving force is not precipitate, gas, or water. The precipitate, gas, or water are the products of those reactions. So they're one and the same. It's also totally fine if you just put down precipitate, or you could put the specific precipitate like silver chloride, or the specific gas like carbon dioxide. So those things are all one and the same. Esther, I can totally give a oops, examples similar to the questions on let's see. Oh, okay. Sorry. Okay. Yes, I can totally. So, Susan, I'm just now seeing examples of yields you're asking for, and Carenza, you were asking if I could put like a long one with multiple parts, so you can like try it, and then we could come back to check. Yeah, totally, we can. Yep, molecular weight problems. I can roll all of these up into the same thing. So here, let me cook up a nice long problem, and then and I won't start working it immediately, and then you guys can ask me when you want to start seeing that problem go live. That way you'll get the experience, the experience of doing it, and then watching me work it, so you can get unstuck. Okay, so nope. All right, so here is our fun time example 1. Let's see. All right. This will be a fun one. So, oops. Iron 3 oxide reacts. Oops. Oh, sorry. Just kicked my desk and it was right under my mic and it was like a loud pop. Kate, I can totally cook up some molecular polarity business. All right. Okay, so iron 3 oxide reacts. Let's see. With carbon monoxide to produce let me just make sure that this will all balance. Yeah. Iron and carbon dioxide. Ah, Esther, great question. Okay. So iron 3 oxide reacts with carbon monoxide to produce iron. Sorry, with carbon monoxide to produce iron and carbon dioxide. Part A, you probably already know. Write a balanced chemical equation. Part B, 4.00 grams of iron 3 oxide are mixed with 1.00 grams of carbon monoxide. Oops. Determine the limiting reagent and theoretical yield of iron, ABC, Part C. The percent yield of iron was 28.3%. Determine the actual yield. All right, so there is an example of well, all the yields really. We've got theoretical, we've got percent, we've got actual all up in there. It's a limiting reactant problem. So go ahead and give that one a crack. Fun time example number 1. Okay, I'm gonna do something. So Kate and Esther have both asked for molecular polarity examples. Oh goodness. I'm gonna do something fun. I'm gonna open up exam 2 and look at the types of molecular polarity questions that I've thrown on there. Just because it's been a minute, I want to refresh my memory, and then I'll pass on something similar to you. Let's see. Hang on one sec. Okay. All right. Sorry, I'm almost done. Dialing up some molecular polarity. Some examples. Okay. So determine if each molecule is polar or nonpolar. All right, and so for compound A, let's do about PF3. B, let's do BF3. Yeah. We can do. We'll do a couple more, but let's start here. All right. So a little bit of info. Let's do the electronegativities of each of these. Boron has an electronegativity of 2.0, phosphorus 2.1, fluorine 4.0. All right, so this is a little, these are numbers that we're going to use because the thing to remember is if you're polar, the central thing to polarity is if you're going to be polar, you need two things. One, you must have polar bonds. Polar bonds are a requirement for polar molecules. But the second thing you need is your central atom cannot have (100%) of the same group on each, I should say, I can make this a little simpler, cannot have the same group on every position of its electronic geometry. All right? You can't have the same group on every position of the electronic geometry. So really, there are two things you have to do to determine if your molecule is polar. You got to calculate the difference in electronegativity, make sure that you do have polar bonds. And then the second thing you got to do is you have to draw the Lewis structure. All right. If you don't calculate the polarity, the bond polarity, you don't know if you have polar bonds. If you don't draw the Lewis structure, you won't know if everything's canceled or if you have different things around your central atom. So, those are the two things we got to do for phosphorus trifluoride and boron trifluoride. All right, let's dive into it. So we're going to do PF3 first. I'm going to change the color. Around phosphorus trifluoride. So first, do we have polar bonds? Our difference in electronegativity here is fluorine's is 4.0, phosphorus's is 2.1. So our difference here is 1.9. All right, these bonds are definitely polar. Remember, polar bonds are between are 0.5 to 2.0. Those are our polar bonds. Definitely polar here. Next, we need to draw the Lewis structure to figure out oh shoot. No. We've got to draw our Lewis structure to determine whether or not this molecule is symmetric. If it's symmetric, perfectly symmetric around our central atom, then it will be nonpolar because those individual bond dipoles will cancel each other out. If it's not symmetric, then we're polar and everything's good. So, we have to calculate our electrons, phosphorus. Whoa. Phosphorus has 5 valence electrons. Fluorine has 7. But we have 3 fluorines in our molecule. So that'll give us a total of, 7 times 3 is 21, plus 5 is 26 electrons total. We're going to select phosphorus as our central atom, and we need to attach 3 fluorines to our central. This is going to cost us 2, 4, 6 electrons out of our budget. Leaving us with 20. Now, to complete the first octet, on fluorine, it's going to cost us 6 electrons. 2, 4, 6 to give fluorine 8 electrons. Leaving us with 14 in our budget. Our next fluorine also requires 6 electrons to get up to 8. So we subtract another 6. And then finally, our last fluorine needs 1, 2, 3, 4, 5, and 6. Leaving us with 2. And the cool thing is, all of our fluorines have full octets right now. Phosphorus does not. So we can give our last 2 electrons to phosphorus. And that is that. All right. Okay, well, when I'm done with this, I can bounce over and we can start cracking on that situation. Let me just check something real quick. Oh, snap. Hang on. Okay, let me finish working this. I just took a look at the problem that I wrote. Okay, so yeah. Let me just wrap this one up, part A. Then I'll go and take a look at that. I may have messed something up there. Actually, I'm pretty sure I did, but I don't know. So stay on the line. Okay, so where are we in this problem? This is where we're at. You'll notice. I gotta double check it. So you'll notice that here on phosphorus, so we have polar bonds. The question is, do we have different groups? And 3 of them are the same, right? 3 of them are fluorides. 1, 2, 3. But the 4th position is a lone pair. If they were all fluorides, they would cancel, it would be nonpolar, but since they're not all fluorides, we need 4 fluorides for that to happen. Since they're not, that means that this molecule is polar. All right? If everything was a fluoride, it would be nonpolar, but since there's that 4th group, that lone pair, that makes it polar, because not everything cancels. Okay, let me just take a look at this example problem situation, just to make sure I didn't ruin things. So Okay. Okay, hang on. I may have messed us up, but if I did, then I'll fix it. Just give me a sec. Okay, just looking real quick. Let's see. Okay. I have low-key bamboozled myself. Just give me 1 second here. Okay, it's not unsolvable. Okay, yeah. Actually, if you can believe it, one of them does. Okay. 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 So here, let's dial things back just for a hot second. Whoop. Where's the problem? There we go. Okay, let me just say this really quick. Even though it is possible to balance this equation, this is harder. Balancing this equation is harder than any reaction on exam 2. All right, I did not mean for it to be harder. I just made up a problem off the top of my head without checking it first, to be honest. And it is solvable. It's not that it's unsolvable. It's just really, really hard. And so anyways, if you're like looking at this and you're like, how would I do that? How would I even know how to... Don't stress about it. Nothing on exam 2 is challenging like this is challenging. So let me give you part A, and then you guys can progress to part B. Oops. Nope. So we have here iron 3 oxide, reacting with carbon monoxide, producing carbon dioxide and iron. All right. Yes, that can totally happen. So here, iron 3, oops, has a charge of +3. Oxide, a charge of -2. So iron 3 oxide will be Fe2O3. Carbon monoxide is just one carbon and one oxygen. Carbon dioxide is CO2, and iron is just Fe. So these are reactants. Now, check this out. This, when you see it, you're like, oh, that didn't look so hard, but it's honestly wicked hard to spot. I wouldn't put something like this on the test, so you don't need to stress. But check this out. So we've got 2 iron, 1 carbon, 3 oxygen plus from iron 3 oxide, and then 1 oxygen from carbon monoxide. Then we have 1 iron, 1 carbon, 2 oxygens on our product side. All right, check this out. You can balance this thing if you multiply both carbon monoxide and carbon dioxide by 3. Here's how. Well, first, multiplies each carbon source by 3, so that doesn't change anything. Second, you multiply this 1 oxygen, your 1 oxygen coming from carbon monoxide, by 3, and you get 3 plus 3 oxygen on our reactant side. On the product side, then you multiply your 2 oxygen by 3, the 2 coming from CO2, to get 6. The last thing that is unbalanced is iron on the product side, but you multiply that by 2. Now you're golden. So this is the balanced chemical equation for part A of that problem. Now, take a crack at parts B and C, because that's good yield reps. I will totally cook up more examples with equations, chemical equations that you can that are on the level of what you'll be asked to balance on the exam. But at least this will get you unstuck and moving towards parts B and C for that first fun example. All right, let's come back here. So we looked at the electronegativity of phosphorus. That's the thing, Carenza, is balancing that problem takes a trick that you just, I haven't taught us as a class how to balance problems with that level of difficulty. And so, because I haven't given you examples on that level, I wouldn't test you on an example on that level. Hopefully that makes sense. A couple people are able to crack it, but also the reason why, if you're wondering, how did that end up in a problem that you just gave us in office hours, I just made one up off the top of my head, and I don't do that with the exam. Like when I write a problem for the exam, I sit down and I work it. But this, I just wrote the problem there and then moved on to the next problem because people were asking me about polarity. So totally, yes, all the applause to Brianna and Esther. So anyways, there are no there's no curveballs like that coming at you on the exam. I'll totally, once I finish this problem, cook up some balancing problems that are like ones you can expect to run into. Okay. we need to do an investigation to see if boron trifluoride is polar or nonpolar. Yeah, totally. Esther, that's honestly, that's exactly how I did it as well. Like trial and error. And on the exam, I'm less interested in you burning time trying to figure out how to balance this one thing. I'm more interested in giving you problems that you can balance in a relatively short amount of time and then move on to get tested on, on other material. Dropping my pen. Okay. So let's look at our electronegativity. Our difference in electronegativity here for boron and fluoride. Fluorine, has an electronegativity of 4.0. Boron has an electronegativity of 2.0. And so when we take the difference here, it comes out to be 2.0, which still is polar. It's the upper boundary for what can be polar, but it still totally is polar. Totally polar. Okay. So now that we know that the molecule is polar, we still need to figure out so we know, sorry, we don't know that the molecule is polar. Now that we know that we have polar bonds, we have to ask, is the molecule polar? To do that, we need to assess our Lewis structure. We need to look at the Lewis structure, figure out if what we're dealing with is polar. So first we need to total our electrons. Boron has 3 valence electrons. Fluorine has 7. So we have to multiply that by 3. 3 times 7 is 21, plus 3 is 24. All right, boron is going to be our central atom. To attach all of our fluorines is going to take 6 electrons, right? 2, 4, and 6. Leaving us with 18. To put on our first 3 electrons, to complete our first octet, we need to put 3 lone pairs on our first fluorine. So subtract 6. Now we have 12 electrons to spend. We need to spend another 6 to complete the octet of our second fluorine. This will leave us with 6 yet again. And then finally, we spend our last 6 electrons to complete the octet of our third and final fluorine. So we are now officially out of electrons, but you'll notice that boron does not have a full octet. So to complete its octet, we take a lone pair off of fluorine and we use it to make a double bond to boron. That way everybody has access to 8 electrons. Now here, Around our central atoms, you'll notice, our central atom, excuse me, that we have three atoms are attached, and they're all the same. We don't have any other type of atom. We don't have any other lone pairs. So all the groups around our central atom is the same. That means that this atom, or this molecule rather, is non-polar. Because even though it has polar bonds, they're all canceled out because there's a perfect symmetry around that central atom. Cool? Okay. So here, let's see where we are. Okay, so let's maybe circle back to that earlier example that I did and work out our yields. Oh, okay, sorry, hang on. Before we jump to that, Esther asked a question. Polar molecules. Ah. Okay. Okay. Let's find this gnarly example. There we go. Okay. Let's see. Okay. So we have our balanced chemical equation. Balanced chemical equation, and we're told that we have 4.00 grams of iron 3 oxide and 1.00 grams of carbon monoxide. And we're told to determine the theoretical yield of iron and the limiting reactant. Okay, so this is two stoichiometry problems, two stoichiometry calculations roll into one. We have to calculate what the theoretical yield would be based on the mass of iron 3 oxide. Then we have to do the same for the mass of carbon monoxide. And then whichever quantity comes out to be less, that is our theoretical yield, and it was produced by the limiting reactant. So, starting with iron 3 oxide, we need to, we need to convert our mass to moles, so that we can convert from moles of iron 3 oxide goodness gracious, I keep putting a 3 as the subscript for iron when it's totally 2. And then we put moles of just straight up iron in the numerator. The ratio here is 1 mole of iron 3 oxide produces 2 moles of iron. Then we convert from moles of iron to grams of iron. And the nice thing here is we simply use the atomic mass for iron, which is 55. Whoa. Or alien gibberish. $55.85. All right, now we just have to calculate our atomic mass for iron, as we already know. Sorry, we don't calculate the atomic mass for iron. We calculate the molecular mass for iron 3 oxide. Iron has an atomic mass of 55.85. And oxygen has an atomic mass of 16.00. Oops. 0.00. All right, and now we crunch our numbers. All right. Here's my calculator. 55.85 times 2 plus 48 is 159.70. This is our molecular mass for iron 3 oxide. And now we cancel everything. Grams of iron cancels grams. Moles of iron 3 oxide cancels moles of iron 3 oxide, and then moles of iron cancel moles. And now we crunch our numbers. 4 divided by 159.70 times 2 times 55.85 comes out to be, rounded to 3 sig figs, 2.80 grams. We don't know if this is the answer. because we need to repeat this calculation with the initial mass of carbon monoxide. So we got to convert grams to moles. Moles of carbon monoxide to moles of iron. This is a 3:2 ratio. 3 moles of carbon monoxide react to make 2 moles of iron. And then we use the atomic mass of iron. To convert from grams to moles. Sorry, from moles to grams. All right. Grams of carbon monoxide. Oh, but start canceling. We still need to know what the molecular weight of carbon monoxide is. Carbon's atomic mass is 12.01. Oxygen's atomic mass is 16.00. We got to add these two together. Comes out to be 28.01. Now we can crunch our numbers. 1 divided by 28.01 times 2 divided by 3 times 55.85. This comes out to be 1.33 grams of iron, and this is our theoretical yield. That is our theoretical yield right there. And that makes carbon monoxide the limiting reactant. All right, and that is the answer to part B. Part C. Oh, let's see. Question. I can. Let's finish up this example, and then we'll do some molecular geometries. All right. Part C to this problem. In part C, we're told that the percent yield was 28.3%. Okay, let's see. Susan, great question. Okay, So our percent yield is 28%. Here, hang on 1 second. The crying baby. Okay. All right. So, there we go. Okay, so we're given a percent yield here. We have just calculated our theoretical yield. In the previous step, which is 0.33 grams. And we're asked to find actual yield, right? We can do this based on the equation for percent yield. It's actual over theoretical all right, and when you look, it's percent. We have percent yield, we have theoretical, so we can calculate actual. We can calculate actual if we do a little bit of algebra. So we got to multiply. We got to get our actual yield isolated on one side of this reaction. We've got to multiply both sides by our theoretical over 100, so they each cancel on the right side of the equation, so we can solve for actual yield. So our actual yield is equal to the percent yield, which is 28.3, times the theoretical yield, 1.33 grams, over 100. 28.3 times 1.33 divided by 100 leaves us with an actual yield of 0.376 grams of iron. And that is that is the end of that large problem that began way back at the start of office hours, or near the start of office hours. Okay, so we had a request for some molecular geometries, which we can totally do. And then there's a couple, I believe it was, chapter 6 practice homework that are up on deck. So we'll hit these sequentially. All right, so for these few examples, let's determine determine the molecular geometry. Determine the molecular geometry for. Let me just refresh my mind to see what's on, say, an exam. Ah. Brianna, they are all different names for the same thing. Formula mass equals molecular weights. Okay. So let's determine the molecular geometry for, and then we'll hit kind of a revolving door of problems. Let's go ahead and kick things off with let's see. How about this molecule? Are there avocado problems? Okay. So let's determine the molecular geometry for this guy. Whenever you're determining the electronic geometry, you've got to look at two things. You've got to look at your electron groups because this will give you the electronic geometry. And then times two. You look at the electron groups because that tells you your electronic geometries, and then you combine this with your number of lone pairs, and that'll give you, together with your electronic, that'll tell you what your molecular geometry is. So, for electron groups, carbon has 4 atoms, 0 lone pairs, the 4 atoms plus the 0 lone pairs together means you've got 4 electron groups. For electron groups makes your electronic geometry. Here, let me just scoot this down. Oh, shoot. So for electron groups, makes your electronic geometry tetrahedral. And whenever your number of lone pairs are 0, that means that your molecular geometry is equal to your electronic geometry. All right, let's see. All right, so here, because we have no lone pairs in play, our molecular geometry is equal to our electronic geometry. So our molecular geometry for this molecule is tetrahedral. Let's do a couple more. Let's look at nope. New slide. Let's look at PH3. Phosphorus trihydride. All right, so here, with our electron groups, here with our electron groups, we have three atoms, one lone pair, so we have 4 electron groups. That makes our electronic geometry tetrahedral. Wow. Okay. Or strange alien scribbles. Tetrahedral. All right. But once you know your electronic geometry, you have to look at your number of lone pairs. And we have 1. So whenever you have one lone pair, combine with a tetrahedral electronic geometry, that makes your molecular geometry trigonal pyramidal. So there's trigonal, pyramidal. I apologize for the slowness at which this is going. Photoshop is getting kind of laggy, and it does this whenever my computer thermals are shooting out of control. So every once in a while there's a stream where the computer gets very hot, and it slows Photoshop down quite a bit. Okay. So this one would be trigonal pyramidal because we have a tetrahedral electronic geometry with one lone pair on our central atom. Let's do one more and then we'll move on, because I know we're getting other types of questions, but I want to do one more here. Let's do a tellurium difluoride. Okay. So let's see here. We have, for our electron groups, two atoms, two lone pairs. So that's 4 electron groups, which means our electronic geometry is tetrahedral. All right. But as we know, when your electron groups are lone pairs, it changes your molecular geometry. So a tetrahedral electronic geometry together with 2 lone pairs means that our molecular geometry will be bent. All right, so this is kind of the process that you have to go through. You look at your atom, your molecule, you look at your central atom, look at the total number of electron groups, that's your electronic geometry, and then from that, figure out how adding lone pairs changes the molecular geometry. If there's no lone pairs, it'll be the same as the electronic. If not, Excuse me. It will change. All right, Kate, I know you asked for some practice drawing Lewis structures, and then there's a bunch of book chapter problems. Let me do this. I'm going to draw up here some example Lewis structure problems. Then I'm going to go do some book problems, and then we'll circle back around, and I'll draw these Lewis structures out for you. So draw the Lewis structure for let's do SO3 with a -2 charge. Let's do NO2 with a -1. Let's do PO3 with a -3. Okay. Okay. So Kate, you can give these a go. See how. Try them on for size. See how they fit. I'm trying to find. There we go. Carenza, you were wondering about Chapter 6. Chapter 6. 76 through 78. All right, and believe it or not, earlier this office hour I actually did 77, so I won't do 77 here, mostly because I already covered it, so you can see it earlier in the video, but I can hit up these others. So chapter 6, number 76. Let's see. Okay, a mixture of hydrazine and hydrogen peroxide is used for as fuel for rocket engines. These two substances react as shown in this equation. So we have hydrazine, which is a cool dude, reacting with hydrogen peroxide. To produce nitrogen and water. All right, and our balanced chemical equation has 2 moles of hydrogen peroxide, and this reaction produces 1 mole of nitrogen gas and 4 moles of water. They tell us, let's see, they want to know what mass of hydrazine we need to react with 35.0 grams of hydrogen peroxide. All right, so this is a stoichiometry problem. We're going to have to do some conversions. So we got 35.0 grams of hydrogen peroxide, H2O2. And we need to find the mass of hydrazine. Now we know the molar ratio is a 2-to-1 ratio. 2 moles of hydrogen peroxide reacts with 1 mole of hydrazine. Before we can use this ratio given by the balanced chemical equation, we need to convert our mass of hydrogen peroxide to moles. Once we have, this is where our balanced chemical equation kicks into gear, because we know the unit conversion for moles of hydrogen peroxide to moles of hydrazine from the balanced chemical equation. And that ratio is a 2-to-1 ratio. Finally, we're not interested in moles of hydrazine, we want grams. And now we're more or less locked and loaded. We just need to calculate the molecular weights of each compound. So hydrogen has an atomic mass of 1.01. Oxygen has an atomic mass of 16.00. There are 2 of each of these in 1 molecule of hydrogen peroxide. So now we can crunch our numbers. 1.01 times 2 plus 16 times 2 gives us a molecular mass of 34.02. All right. We got to do the same thing for the molecular mass of hydrazine. Nitrogen has an atomic mass of 14.01. Hydrogen, as we already know, has an atomic mass of 1.01. We've got 2 nitrogens in 1 molecule of hydrazine. We have 4 hydrogens in that same molecule. So we multiply each atomic mass appropriately. 14.01 times 2 plus our 4.04 is 32.06. When you look, everything that needs to cancel does. Grams of water cancels. Oh shoot, hang on. Sorry. It looks like my computer got unplugged. Which means that my battery's dangerously close to dying. That also might explain some of the performance struggles it was going through, because it's probably, oh my gosh, yes. It's going, I'm dying, I'm trying to save power. And I'm like, work, stream faster. Just plug me in, I'll do what you want. If you're wondering what you're watching, yes, you're watching your chemistry instructor have a conversation with his computer. Now that everything cancels, let's crunch our numbers and find out how many moles of hydrogen peroxide how many grams of hydrazine we need to react with 35 grams of hydrogen peroxide. 35.0 divided by 34.02 divided by 2 times 32.06. The value that I'm getting is 16.4917. 7, but I can only keep 3 of these sig figs. 9 will round up. So I've got 16.5 grams of hydrazine are needed to react completely with 35 grams of hydrogen peroxide. Okay, let's see here. Okay, chapter 6. Okay, yeah. Yep, we'll totally jump to the chapter 5. We just got one more in chapter 8. And then we'll hop on over to chapter 5. Okay. Oops. No. Chapter 6. I'm number 78. Again, I'm not skipping 77. We just did that one at the beginning of office hours. So, we're given a reaction that's already balanced, which is nice. Is that? Yep. And HCl. Okay, and we are asked to determine the grams of hydrochloric acid that would be produced if 25 grams, 25.0 grams of potassium bisulfate is produced at the same time. All right, so classic stoichiometry. We've got 25.0 grams of potassium bisulfate. We actually know what our molar ratio is here. If you look at it, it's a 2 to 8 molar ratio. But to use that, we first have to convert grams to moles. Grams of potassium bisulfate to moles. Then we convert from moles of potassium bisulfate to moles of HCl. And here, this is a 2 to 8 molar ratio. And then finally, we convert from moles of HCl to grams of HCl. All right. Potassium, here's what we don't use a ton, has an atomic mass of 39.01. Hydrogen, 1.01. Sulfur, 32.07. And oxygen, 16.00. But we have 4. So we got to multiply that 16.00 by 4. So 16 times 4, 64 plus 32.07 plus 1.01 plus 39.1 is 136.18. Oh my gosh. Photoshop is reacting so much better now that I plugged my computer in. I didn't even know it was unplugged. It's really nice. Okay. Now let's look at HCl is the only unit conversion we need. Hydrogen's 1.01, chlorine is 35.45. So we add these two together, come out with 36.46. Corinza, let me finish this problem, and then I'll answer that question. 36.46 grams of HCl are in 1 mole. All right, so now grams of potassium bisulfate cancel, moles of potassium bisulfate cancel, and moles of HCl cancel. Ready to crunch our numbers. 25 divided by 136.18 times 8 divided by 2 times 36.46. This equals 26.77333882. We can keep 3 sig figs. That 7 will round up. So the amount of hydrochloric acid produced alongside potassium bisulfate will be 26.8 grams of HCl. All right, that is the answer to that is the answer to chapter 6, number 78. Okay. So, Corinza, first off, though many double displacement reactions do produce a solid, there are some that produce a gas or molecular water. So you don't have to produce a solid to be a double displacement. There's some that make gases. There's some that produce molecular water. So, for example, reaction 6 from lab 7 is a double displacement whose driving force is the formation of water. Okay, and then 2, how do we know if a set of reactants will not result? Okay, great. Great question. If every, and I'm going to put this in parentheses, product of a double displacement is okay, let's see. So they could produce 2 non-solid compounds. Um, um, yes, as long as okay. So with all of these, okay, let me just take a look at number lab 7. Okay. Okay. So Corinza, the thing is, they cannot both be ionic aqueous compounds. Remember, all precipitates are ionic compounds. Okay, and then, Corinza, your question, how do we know if the product is aqueous if it doesn't tell us? So, you base your decision on the observations Okay. All right. So there's a handful of questions from chapter 5 that we're finally swinging around to. Let's see, chapter 5, 93, B and C. Oh, and 90, sorry. It's chapter 5, number 93, B and C. And then we have chapter 5, 95, A and B. Okay. Let me take a look at quiz 7. Let's see. Lab quiz 7. Let's see. There's that one, and then actually, okay. So you totally could use solubility rules. But you actually don't have to. All the reactions in that question are from lab exercise, are from lab exercise 7. So you actually had the chance to observe them. Okay. So let's see. So we've got some questions on a few chapter 5 things. Chapter 5, number 93. How many numerical prefixes are present? Here, I'm just going to write this down. In the following, okay, good. Carenza, you are welcome. Okay. Okay, so, and then part B. And part C. So for part B on number 93, it's H2S. And part C is HI. Well, let's name these dudes. First one would be dihydrogen monosulfide. So this would have, oh, I just wrote how numerical prefixes. How many? How many numerical prefixes? So, since we're being asked how many, there are 2. For HI, this would be hydrogen. Monoiodide. So there's only one numerical prefix. Just one. All right, that would be 93. Parts B and C. Let's look at 95. This says name. Name the following. Yes. Totally. So, here, hang on. So there is a rule where you let's see. Here, hang on one second. I'm gonna go check on my baby. Hey babe, I know I just have 15 minutes left. If you just hang on for 15, I'm ready to feed him upstairs. I'm just saying. I don't know if you could feed him somewhere else or maybe in the other room. Maybe that might be really Okay, so, Carenza, to answer your question, of why the book says 0 for both, there is a commonly accepted shorthand where you don't use prefixes for compounds that start with H. And I didn't teach it to the class on purpose. Because compounds that start with H, let's see. Compounds that start with H are acids. So they have a completely different way of naming. Completely different system. That we will learn in chapter 10. Okay, that is the long drawn out thing. Compounds. The short of it is I typed most of this, but this is the short verbal summary. Compounds that start with H are actually acids. Acids have a different way of naming. There's a different system for naming acids than normal covalent compounds. Acid-based chemistry is until chapter 10. So we'll get to naming acids when we get to chapter 10. For now, you can name them like normal covalent compounds, and that's all you need to know. And I'm pretty sure this will echo into this one, chapter 5, number 95A and B. It says name the following. Oh, all of which have common names. You don't need to know the common names. But yeah, totally. And I'm sorry for the confusion there. H2O2 and B is NO. So just using our normal covalent naming system, this would be dihydrogen, dioxide, and this would be nitrogen, monoxide. So that is how you would name both of those dudes. All right. Let's see. think we are. I am current with questions at this moment. We have about 10 minutes left, so that's enough time to pop off a quick few questions. That is, if you have any other questions. That is correct. If you want a quick and just kind of easy way to identify the diatomic gases, you can take a look at the periodic table. They're all right here. Yeah, you're welcome. And if you want to see more, they're all right there. And hydrogen. These are all your X2 gases. They all kind of are all just chilling on this corner of the periodic table. And then hydrogen's just a guy. You just kind of have to remember him. But everybody else is right up there on that corner. Alrighty, well, I think we're gonna call that an office hour. Thank you everyone for coming out. I am wishing you all nothing but the best of luck on the exam. It's gonna be a challenge, so do your best. Don't forget at the results. Making it through a summer session takes courage, and this will definitely be a test of all of our courage. I'm sending you all the positive vibes. Listen to my emo playlist. It'll get you through all right. Okay, I hope you all have a good weekend. Study hard, do well, and I'll catch you all on Monday.